In this video series, we're going to take a look at L'Hopital's rule, not La Hospital's rule, but pronounced L'Hopital's rule. And L'Hopital's rule is going to be a rule that's going to help us to evaluate limits by utilizing derivatives if they're in this thing called an indeterminate form. So the three main topics we have to look at are what is an indeterminate form, what is L'Hopital's rule, and then the techniques for applying L'Hopital's rule. So let's first of all look at these things called indeterminate forms. And an indeterminate form is any time that you evaluate an expression and you get one of the three following basic types of indeterminate forms. So you either get 0 over 0, you get infinity over infinity, and then finally, the opposite of infinity over infinity. If you get one of those three forms, that means that you can apply L'Hopital's rule. All right. And L'Hopital's rule says that if lim as x approaches a of f at x over g of x, so a rational function, produces an indeterminate form, all right, then what we can do is we can evaluate this by taking the derivative of the top and the derivative of the bottom. So that's lim as x approaches a of f prime of x divided by g prime of x. Now, that does not mean to use the quotient rule. Okay, so do not use the quotient rule. All right? You're going to use L'Hopital's rule to be able to evaluate this. And so essentially what we're going to do is we're going to first see if direct substitution produces an indeterminate form. All right. And if it does, then we're going to use L'Hopital's rule. And we might have to use it more than once. So we might have to use it 2 times, 3 times, as many times as we keep getting an indeterminate form. For the first few examples, we're just going to take it easy and only use it maybe once or twice at most. So let's take a look at a very basic example to where we could have evaluated this by using an old technique, but we can see how L'Hopital's rule applies. So let's go ahead and evaluate this limit. X approaches -6 of x squared plus 13x plus 42 divided by -48 minus 2x plus x squared. So let's try direct substitution first. All right, and this is what we did all the way back in chapter 2. So by direct substitution, we would have -6 squared plus 13 times -6 plus 42. And we would divide that by -48 minus 2 times -6 plus -6 squared. And in the numerator, that would be 36 minus 78 plus 42. All right. In the denominator, that would be -48 plus 12 plus 36. And what does that yield? That yields 0 over 0. And that's an indeterminate form. All right. So what that means is that we can use L'Hopital's rule. Right? And here's how we're going to do that. We're going to take the derivative of the top and the derivative of the bottom. Whenever I put an L with a circle in it, that means I'm using L'Hopital's rule. All right? So if you see that, that just means I've used L'Hopital's rule. And so the derivative of the top, so now it's going to become lim as x approaches -6. Now notice the derivative of the top. It's going to be 2x plus 13. Okay, so I'm just taking the derivative of this. And then the derivative of the denominator is going to be -2 plus 2x. Now we can go ahead and substitute -6 in. Okay, so now we're going to try direct substitution. That's going to be 2 times -6 plus 13 divided by -2 plus 2 times -6. And that's going to yield -12 plus 13 is 1. -2 minus 12 is -14. 14. So we're going to end up with negative 114. Right? Now, just to illustrate that we could have done this using the old technique. Okay, so let's see if we can get the same by factoring. Now, what I'm going to do is I'm going to rewrite the polynomials in the numerator and denominator. All right, so I'm going to write them in descending order of power, the usual way we write it. So this is going to become lim x approaches negative 6. The numerator is nice and set up for us. X squared plus 13x plus 42. And the denominator, I'm just going to rewrite it as x squared minus 2x minus 48. And now we're going to factor the numerator and factor the denominator. All right, so this is going to become lim as x approaches negative 6. The numerator can factor into x plus 7, x plus 6, which is nice. The denominator can factor into x minus 8, x plus 6. And we remember from the very first sections that we can cancel those out. And now we can try direct substitution. So we're going to get negative 6 plus 7 divided by negative 6 minus 8. The numerator becomes 1. The denominator becomes negative 14. Clearly, we get the same answer. All right. This is an example to where L'Hopital's rule is probably not as beneficial as factoring. All right. In fact, they probably take about the same amount of time to be able to work with. However, L'Hopital's rule applies, as does factoring. So we can go ahead and just check the answer. Now, in later examples, we're not going to be able to check the answer. We're just going to have to rely solely on L'Hopital's rule. And of course, we could per se check the answer by utilizing our calculators. All right. And just to remind you that what we could do is we could graph this function. All right. And we could see what happens around negative 6. So let's just do that real quick, just to remind you, because it's been a little while since we've worked with limits. So I'm going to go into the calculator. I'm going to go to y equals, and I'm going to graph x squared plus 13x plus 42. And we're going to divide that by x squared minus 2x minus 48. All right, it's going to give us a weird looking function, I'm sure. All right, so let's graph it. And I'm going to zoom standard. All right. And what we're going to do is we're going to look and we are going to zoom. So let's trace the function. And I think it's pretty obvious if we were to trace it and move over. So let's move over a little bit. I'm just going to trace this. All right. And oh, we need to go towards negative 6. I was going towards 6. That wasn't smart. All right. So I'm just going to trace this until we get to negative 6. So it's going to take a little bit of time. So just hold tight as I get this closer to negative 6, and then I'm going to zoom in. Oh, I just passed it. So that's pretty close. So I'm going to zoom in right here. So you might remember this trick from the very beginning when I showed this to you. And I'm just going to zoom this, and I'm going to graph this, and I'm going to trace it. And let's see if I can get, all right. So, and I'm going to zoom in one more time. All right, so we'll trace it, and we're a little bit over, so we need to go to the right. So this is really, really close, negative 5.997, and we get negative 0.07163. So let's see what 1/14 is, and let's see if it's close to that 0.07163. So we're going to quit, and let's type in negative 1/14. And we get negative 0.07142. Remember when we graphed it and we traced it? Negative 0.0716. All right, so we're really, really close. So that means that negative 1/14 is a pretty viable answer. So I always encourage students to try to check your answers. And now we know 3 ways to evaluate this limit. We could certainly do it by using the calculator. We could certainly do it by factoring, but now we know a new way, which is this L'Hopital's rule. Okay, so in subsequent videos, we're going to take a look at more extensive use of L'Hopital's rule. And of course, you should use your calculator and other methods to check when appropriate.